Hello, Amos Peter is my name, and you are welcome to this lecture titled Computer Architecture. In this course, we shall try to explain what computer architecture is, who are computer architects, and what computer architects do. The main objective of this course is to help students learn and appreciate computer architecture with an emphasis on systems design, performance evaluation and analysis, and to also elevate the thinking process of the student to the level of performance improvement techniques for current and previous systems architecture. So we shall begin with an introduction. There's no doubt that the whole world is undergoing a computer revolution. And it so happens that each time a computer cost improves by, say, a factor of 10, the opportunities for computers multiply. Applications that were considered to be economically infeasible suddenly becomes practical. And it will interest you to know that in the recent past, the following applications were actually considered to be within the realm of science fiction. An example is computers in automobile. Until microprocessors improved dramatically, price and performance in the early 1980s, computer control of cars was a laughable matter. But it will interest you to know that in virtually all the cars that were manufactured, let's say between the year 2000 or even as far back as 1996 up to this moment, computers helps in the reduction of pollution. They help cars not to skip off the road dangerously. Now, another important application is the cell phones. Who will have dreamt that advances in computer systems will lead to mobile phones, allowing person-to-person communication almost everywhere in the world? There's no doubt today that a larger percentage of the world now of the world possess a cell phone that can be used to communicate. As a result of the advances in computer system and their availability, the Human Genome Project, which hitherto will have been able to cost billions of dollars or naira, has now been made very, very possible. Another area that the revolution in the computing technology has made very realizable and easy to access is in the case of the World Wide Web, which was not in existence some years ago. The World Wide Web has transformed our society. And for many, most especially people within the academics, the World Wide Web has now replaced libraries. We also have the search engines, and as the content of the World Wide Web grew in size and in value, finding relevant information also became increasingly very, very important. This very particular picture attempts to show you how we've come thus far in the development of computer systems. Now, if you look at on the left-hand side of the system, This was a computer system that was first booted in the year 1952, and it was designed by John von Neumann and some members of his team. Now, these very computer systems were actually made up of vacuum tubes, which are devices that looks like little light bulbs. And it is actually those light tubes that actually performs the computation that forms the bulk of the electronic circuitry of a computer system as far back as the late 1940s to 50s and 60s. Now, it will interest you to know that this very particular computer that was first booted in Princeton was actually the size of a room. Now, here at the top right of this slide, I'm sure you all see something that will have surprised a lot of the younger generation now. Now, this was a hard disk that is just 5 megabytes, in 1956, and you could imagine how large and colossal it is. You can even imagine the number of people that are trying to move or transport these hard disks to where it is expected to be used. But a quick fast forward at the bottom left will now make you to begin to wonder at how fast and rapid the world has moved. Now, this is a 1 terabyte micro SD card that is several million times bigger than how a storage medium actually looks way back in 1956, which is just 5 megabytes. Here you can see that the 1 terabyte micro SD card is just some few centimeters, 1 inch long. Now, the previous chart was just trying to let the student appreciate how computers look like then. But now, as a result of advances in the microelectronics and chips design, you can now see that in our current or present dispensation, computers now appears in different forms. We now have computers in sensor networks. Most of your digital, in fact, all of the digital cameras in use today also have microprocessors at their heart. We have the smartphones, your mobile audio players, your laptops. We also have autonomous cars that have already sprung up in some other parts of the world, where the cars are able to drive themselves without a physical driver. We also have computers in the form of servers, such as those used for hosting of websites and large files. We also have computers in game players. Computers are also present in routers, flying UAVs, that's unmanned aerial vehicles, the global positioning system, e-books, tablets, and set-top boxes. Here, we want to see a broad set of classes that our computing applications can fall into. And broadly speaking, computers are used in 3 main different classes of applications today. The first one, and perhaps the most popular ones that virtually every student is conversant with today, are the desktop computers. And these are characterized by the personal computers in the form of laptops, palm tops, or the bigger desktop computer system. Now, another important class of for computing applications are the servers and they are the modern form of what were once the mainframes computers, or the mini computers and the supercomputers. And these server computers are usually accessed via a network connection. And then the last but not the least are perhaps the largest class of computers today. And these are called the embedded computers, because they are computers that are actually embedded into virtually every non-electronic component you can imagine today. For example, we have the embedded computers in our digital TVs and set-top boxes. Embedded computers are present in our automobiles, digital cameras, music players, and your microwave ovens. And it will interest you to know that embedded computers will continue to find usage in virtually every technology that is upcoming. So, what is computer architecture? Now, there are various definitions of this term computer architecture, but I would like to give us a few definitions that I think will suffice here. Computer architecture in computer engineering or computer science can be defined as a set of rules and methods that describe the functionality, organization, and implementation of a computer system. Or you may even look at a computer to computer architecture as a set of detailed descriptions that specifies how a set of software or hardware technology interacts with one another in order to form a computer system. Now, generally speaking, what computer architects tried to do is to try to take an application that humans want to execute and then transform it or translate it to what the physics can do. And what do I mean by what humans want to do? Assuming you want to play a piece of music or a video on your computer system, or you want to calculate a spreadsheet using any of the spreadsheet application such as Microsoft Excel or SPSS. Now, what computer architects tried to do is, how do we translate what the humans want to do into what the physics can't do? Because we all know that ultimately, at the basic heart of a computer system are electronic circuitry consisting of transistors, capacitors, and other electronic devices whose native language is what? Zeros and ones. And of course, within the interconnecting wires, you also have photons and electrons bouncing up and down, interacting with one another. So basically, what the computer architecture as a discipline intends to do is to bridge the very wide gap between the application that computer users intend to do and link it up to what the physics can do. And the gap between the application and what the physics can do is actually a very huge or long gap. So the computer architect tries to design the various implementation layers that allow us to execute information processing application efficiently using manufacturing technologies. And I want us to take note of what I mean by abstraction layer here. By definition, abstraction is the act of representing essential features of a system without including background details or explanation. And abstraction is often used to reduce complexity and allow efficient design and implementation of any complex network. And in this slide, we tried to depict what the computer architect intends to do, just like I mentioned in the previous slide. The first thing is, like I said, the application layer. And then the last is what the physics or the physical layer can do. And of course, the aim of the computer architect is to design a set of abstraction layers that helps, the would-be computer user execute the information processing easily and efficiently. And in this next slide, we shall see all the different layers that helps in carrying out the information processing efficiently in computer architecture. So just like I mentioned, at the very bottom here, we have the physics. The physics, I told us, is where the electrons and the photons interacts with the outside world. And of course, using the natural laws of physics, we'll be able to engineer what we refer to as the devices. We'll be able to engineer what we called devices, which are the discrete components that usually make up electrical or electronic circuits. And from the discrete components, of course, we can create electrical circuits. Now, from these circuits, we can build gates, logic gates, like the AND gate, the NOR gate, the OR gate. And of course, using these gates, we can, that takes us to the next layer, which is the register transfer layer that implements languages such as the VHDL and Verilog. And of course, moving up, we have the microarchitecture, or what some people refer to as computer organization. And next, above the microarchitecture layer, we have the instruction set architecture, which actually is the layer that defines all the sets of codes or languages or the instructions that a computer system can execute or do, and it actually serves as the interface layer between the hardware level and the software interface. And on top of the instruction set architecture is where your operating system or your virtual machines lies and operate. While above, we have the programming language. And here, the programming language usually used in this case refers to the high-level language, such as your Python, your C++, Java, or Visual Basic. And of course, at the top, we have the algorithm. And then at the very top, we have the application layer. So whichever way you actually want to go through, either from the bottom up or from the top bottom, these are all the sequences. Whatever you are able to do as a computer user today, these are the logical distinct layers that the information will have to pass through before the physical computer hardware will be able to carry out what you are doing as a computer user. Now, in the discipline of computer architecture, computer architects or architecture generally falls within these three basic layers here. That is where we have the instruction set architecture, the microarchitecture, and the registrar transfer level. However, it will be impossible for you to fully discuss or explain computer architecture without sometimes making excursion a little bit above and below the three layers. So in the process of this course, sometimes we shall make excursions into the operating system and the virtual machine layer, and also the gates layer level. Now, in the previous slide, while I was talking about the three layers that majorly constitute computer architecture, I refer to as the ISA layer, instruction set architecture layer, the microarchitecture layer, and the registrar transfer layer. The microarchitecture, like I said, is also referred to as by some others as the computer architecture. Now let's attempt to explain what computer organization. Let's attempt to explain what computer organization means. And basically, computer organization refers to the operational units of a computer system and their interconnections that realizes the architectural specification. And I will attempt to give an explanation of what I mean by that. For example, it is an architectural design issue whether a computer will have a multiply instruction. So when computer architects want to design a computer system, especially the microprocessor, in the process of determining whether or not that very particular microprocessor will have a multiply or a divide instruction, it is an organizational issue whether that very particular instruction, the multiply or the divide instruction, will be implemented by a special multiply unit or by the method of repeated addition by simply using the add unit of the system. So while the computer architect is mostly concerned about writing out or reading out the detailed description or specification of all the different sets of instructions that the computer system deals with, the computer organization is concerned on how those physical units are being arranged, their sizes, the type of interconnecting wires that connects them, and how they interact with one another. So in other words, the computer architect reels out a detailed description while the computer organizer realizes what has been spelled out in the specification that has been specified by the computer architect. In this very particular table here, we just make an attempt to put on a fly the difference between computer architecture and computer organization, and I will just quickly run through them. On the left hand side, it says the computer architecture Computer architecture is concerned with the way hardware components are connected together to form a computer system, while computer organization is concerned with the structure and behavior of a computer system as seen by the user. Architecture acts as the interface between the hardware and the software, while computer organization deals with the components of a connection in a system. Computer architecture helps us to understand the functionalities of a system, while computer organization tells us how exactly all the units in the system are arranged and interconnected. A programmer can view architecture in terms of instruction, addressing modes and registers, whereas organization expresses the realization of the architecture. Computer architect deals with high-level design issues, while computer organizations deals with low-level design issues. Architecture involves logic, that is instruction sets, addressing modes, data types, cache, memory optimization, while organizations involve physical components, circuit designs, adders, signal processing, and the other peripherals of the computer system. Now, this slide also attempts to just gives us some basic attributes or properties or characteristics of computer architecture and computer organization. And here they are. The computer organization deals with instruction sets, like I mentioned previously. Computer organization also deals with the I/O mechanisms, that's the input-output systems, how the computer takes in information and how it spits out information to the outside world. The architecture also deals with the techniques of memory addressing. That is how the computer accesses information from the computer memory and then moves it to the microprocessor for processing before it's been sent out to the output device. Computer architecture also deals with the number of bits used to represent various data types, such as numbers and characters, while organization, on the other hand, involves the hardware details that are transparent to the programmer. It also deals with the various control signals that dictate how all the various units of the computer system, the microprocessor, the memory, the I/O devices, interact with each other in unison in order to synchronize how information or data processing takes place in the computer system. Organization also deals with the interfaces between computers and peripherals. And computer organization is also concerned with the memory technology that is used in a computer system. So I will want to call it a day in this very particular lecture. That's the introductory lecture, and I hope that the information I have passed in this video has been very, very informative, and I will like you to look forward to my subsequent videos in the subject of computer architecture. So I would like to thank you for viewing.